Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, so firstly, looking at the different features of a wave. So we have got some different diagrams here, and we need to decide which diagrams show amplitude and wavelength correctly. So let's look at diagram A first. So here, the wavelength is between two crests which are next to each other, so that is correct. However, the amplitude is not all the way from a crest to a trough, but from the horizontal line to a crest, so that's not correct. Okay, let's look at B. So this time our amplitude is correct from that horizontal line to the crest, and our wavelength is correct because those are two crests which are next to each other. Good. Okay, now let's look at C. So this time amplitude's been drawn incorrectly here. Okay, it's nothing to do with the horizontal axis, all to do with the vertical one. And my wavelength here, those 2 points look like they could be identical. However, if you look at the first one, the wave is just about to go up after that first point. And if you look at the second one, the wave is about to go down. So be careful, even though these 2 points are both along that horizontal line, they're not identical points, so that is not a wavelength. Okay, and part D here. So we do have two crests, but there's another crest in between them. So those aren't two crests next to each other. That's actually 1.5 wavelengths. Sorry, not 1.5 wavelengths, 2 wavelengths. And the amplitude there is absolutely fine to go from the horizontal down to the bottom. Okay, so that is the correct amplitude. Okay, and now for E here, that wavelength is one whole wavelength because those 2 points, the wave's just going to go down from both those 2 points. So those are identical points, and the amplitude is correct. So that is correct. And for F, amplitude incorrect, okay, because it goes all the way from the top to the bottom. That's not right. And wavelength is along that horizontal axis. So even though that's kind of showing one whole wave, it's not the wavelength, the length there. Okay, draw an appropriate wavefront diagram. So you just need to remember that your wavefront diagram is a set of parallel lines, and those lines line up with where my crests are. So it should look something like that. And I've drawn the arrows there and wavelengths to show that the distance between those lines is one wavelength. Okay, and in this question, we have this time been given a wave which has a time along the x-axis in minutes, and I need to find the time period and frequency. So the time period is the time for one complete oscillation. So first, I need to identify one complete wave. So you can pick any 2 points that give you a wavelength. I'm just going to pick, for me, the most obvious, which is the first crest to the next crest, and that is between 3 minutes and 11 minutes. So that is a total of 8 minutes to go crest to crest. So that's my time period in minutes, but I'm going to convert that time period into seconds, okay, by multiplying by 60. Because in order to use my equation which relates my frequency to my time period, remember my frequency is 1 divided by my time period, I need that time period to be in seconds. So that's 1 divided by 480 is 0.002 hertz, because hertz is my unit for frequency. Okay, now some practice finding wave speeds. So my first question here is find the velocity of a wave with a frequency 50 hertz and a wavelength of 10 meters. So as always, I'm going to pick my correct equation. Speed is frequency times wavelength. Then I have my frequency and my wavelength, so I just need to multiply those two things together, and that gives me a speed of 500 meters per second. Okay, next question. Find the velocity of a wave with a time period 3 minutes and a wavelength 10 meters. So I'm eventually going to be using this equation again. Speed is frequency times wavelength. And I've been given the wavelength of 10, but I haven't been given the frequency. Luckily, I know another equation to get the frequency, given that I've been given the time period here. So I'm going to use that equation that frequency is 1 over time period and say that my frequency is 1 divided by 3 times 60. Remember again, that time is in minutes and I need it to be in seconds to use that frequency time period equation. Okay, so that gives me a frequency of 0.00556. To find the speed then, I multiply my frequency by my wavelength, which was 10 meters, gives me 0.056. Oh, I put meters there, I mean meters per second for my speed. Okay, and finally, find the velocity of a wave that travels a distance of 10 kilometers in 30 seconds. So this is just to remind you that sometimes, even when you're looking for a wave velocity, you are just using distance over time. So all I need to be careful with in this question is that my distance, need to convert it into meters at 10,000 meters, divided by 30, 333 meters per second, okay? Which actually incidentally is roughly the speed of sound in air. So I might be able to infer from the answer that I get that this could be a sound wave traveling through air. Okay, now to look at some question involving echoes. So we have a student smashing some cymbals together and they are 600 meters away from a wall. The student hears the echo after 3.6 seconds. How fast was the wave? So I'm just going to draw, and I would always recommend doing this, a quick diagram. So that dot is my student, the wall is 600 meters away. Okay, so then what information do I have? I have the total time is 3.6 seconds. And I can figure out the total distance, remembering, okay, and this is why my diagram sort of helps me, that the wave had to travel all the way to the wall and back. So it is actually 2 times 600 is 1200 meters. And then I use my classic equation for speed, distance over time, 1200 divided by 3.6 is 333 meters per second. Okay, a pulse is sent down a hole in the ground. To find the depth of the hole, the velocity of the pulse is 5 meters a second. Time taken to re-receive the pulse is 40 seconds. How deep is the hole? So again, I'm going to draw a quick diagram to remind myself that that wave is going all the way there and all the way back. And what information do I have? I have the speed and I have the total time. So the total distance is going to be the speed multiplied by the time, which is 800 meters. And then I look at my diagram and think that's not the depth of the hole because that is the distance going all the way down and all the way back. So actually, in order to find that depth, I need to divide that distance by 2, and that gives me 400 meters. Okay, on to the nature of a wave. So explain how to find the speed of a water wave on a lake. So you need to take the distance between 2 points, probably make the distance as large as possible to reduce the errors here. And you need to measure that distance, so however many meters that is. Then you need to watch one particular wave, so maybe the crest of one particular wave, and you need to time it between those 2 points. Then you use speed equals your distance between the 2 points divided by time. Okay, people suggest the way you hear sound waves is air particles near the source of sound get disturbed by the vibration and travel to your ear. Explain whether the student is right or wrong. So we should know that the student is wrong because we should know that the matter, in this case the air, doesn't move with the wave. How do I know that in the context of a sound wave? Well, if the air were to move with the wave, then whatever was creating that wave, you'd be left with a vacuum around that source of sound, which you don't get. So the air stays where it is and the wave moves through the air, okay, to your ear. When I say that the air stays where it is, what I mean is it doesn't move with the wave. It still does get disturbed by the wave, but it remains in the same position that it was in before.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Hey, tips and tricks for this section. Echoes, look out for the fact that you're dealing with the total distance, okay? So if you are given the total time, remember that that is the time to go there and back, okay? And if you are given the distance to the surface, then remember, if you're using your equation, you've been given a time and you've been given the velocity, you need to make sure that you double that distance so that it's going there and back in that time. Okay, amplitude, yeah, it's not from the bottom of the wave to the top of the wave. That's just the most classic mistake that students can make for amplitude. Make sure it's from that horizontal line. And use a sense check. The speed of sound is roughly 330 meters per second, and the speed of light is 3 times 10 to the 8 meters per second. So if you're supposed to be working out the speed of a sound wave and it is wildly different from that in air, then recheck your calculations. You've probably done something wrong. I just want to add a quick extra tip here, which is if you are using that frequency as 1 over time period relationship, make sure that your time period is in seconds before you use that. Otherwise, your frequency won't be in hertz.